Okay, so now that we've found the slope field, that gives us an approximation of what the function looks like, because a lot of times in differential equations we can't actually differentiate or we can't solve the differential equation, and so slope fields are like this extra tool that helps us visualize what the function probably looks like. In this case, and in the case of all of the ones we're going to use in AB calculus, we are going to be able to differentiate these differential equations, at least for any differential equation I give you, we just do separation of variables. That's all we're doing in AB calculus. But the slope field helps us visualize. So we visualize that they are a semicircle. Okay. Now let's solve it and see if that's true. So we're going to separate the variables. So I'm going to multiply y by both sides, and I get y dy equals negative x dx. Now I'm going to integrate both sides, and I'm going to get y squared over 2 equals negative x squared over 2 plus c, we'll call that c1 because we're probably going to get some more c's, right? So then we multiply both sides by 2, and we get y squared equals negative x squared, and already we have a new c plus c2, and then we take the square root of both sides. And so we get y equals plus or minus the square root of negative x squared plus c2. So what are our two functions that come from this differential equation? Well, it's positive square root of negative x squared plus c2 and negative x squared plus c2. So those are our two functions, and do those represent what we found in the first example? Yeah, those are semicircles, right? And so we found a semicircle. So we in fact have the equation and the slope field to support that. So now these are general solutions, remember, because they still have a constant in them. We'll just go ahead and write C there on that one. All right, so we want to find the particular solution for the differential equation whose graph passes through that point 0, 1 that we graphed one from. So the particular solution, remember, we're going to use one of these two because we don't actually know, we either use this one or this one. Now, this has a y value that is positive, right? So the output of this function is positive. Which one of these has a positive output? Well, this one, right? Because this has a negative output because whatever's inside of here has to be positive. So that's going to end up negative times a positive, and this is going to be positive times a positive. So we're going to use our first one. So y equals the square root of negative x squared plus c. And then we're going to plug in the point to figure out what c is. So we have 1 equals the square root of negative 0 squared plus c. Well, negative 0 squared is just 0. So we have 1 equals the square root of c, so c equals 1. So our particular solution is this y equals the square root of negative x squared plus 1. That would give us the actual semicircle that's going to give us that. And that's basically what we found here, right? We found a semicircle that has about a radius of 1. Mine's maybe a little wider than I should have made it, but it has a radius of about 1. Okay, so let's look for the particular solution for this one. Now, this has a y value that's negative, which means we're going to use this function instead. So, y equals the square root of negative x squared plus c. And then we just plug in our y and x values. So we have negative 3 equals the square root of 0 plus c, which is just c. So we square both sides, we get 9 equals c. So c equals 9 in this case. So our particular solution is y equals, just kidding, I used the negative one. Which, let's see if that changes anything. I can't remember. Nope, we still end up with positive c because we square both sides. Yeah, we still square both sides and we end up with positive. But see, don't want to forget the negative. Okay, so y equals negative the square root of negative x squared plus 9. So that's our particular solution, and that would be a semicircle with a radius of 3, and that's what we had graphed. Okay, so we have another differential equation. We want to go ahead and draw the slope field, a dot plot at the right, and then we're going to graph it. So this it says y prime equals 1 over y. I'm trying to find myself some room. All right, we'll just have to erase this here in a minute. Okay, so y and y prime, because this doesn't depend on x, right? It doesn't matter what x is, it only matters what y is. So when y is 0, y prime is undefined. When y is 1, y prime is 1. When y is 2, y prime is 1/2. When y is 3, y prime is 1/3. When y is negative 1, it's negative 1. When y is negative 2, it's negative 1/2. And when y is negative 3, we get negative 1/3. Okay, so this does not depend on x at all, right? So it doesn't matter what x is, it only matters what y is. So I'm going to come over here where y equals 1, and everywhere that y equals 1, y prime equals 1. So everywhere that y equals 1, y prime equals 1. So I'm going to try to start by giving myself like a little, maybe I will do that line thing. There's a line, okay, and then I'm going to draw, yeah, that's super straight, Mrs. Barney. Man, straight lines are not my forte, that's probably why I don't teach geometry, right? Okay, so everywhere that y is equal to 1, we're going to have a slope of 1. Okay, even where x equals 0, right? Because x doesn't matter. All right, when y equals 2, y prime equals 1/2, so it's going to be a little bit shallower here. And then when x equals 3, y prime is equal to 1/3, so it's even more shallow. Okay, then when y equals negative 1, we have a slope of negative 1, so it's going to be like that. And then negative 1/2. And then negative 1/3. Okay, there's our slope field. Now when y equals 0 along the x-axis right here, along the x-axis, does our function have a derivative? Nope. Nope, so no slope there. Okay, so draw the slope field, graph the particular solution passing through the points negative 2, negative 1, and 2, 2 as functions of x, which means they have to be functions. They have to pass the vertical line test. So let's see. We're going to pass through the point, what did I say, negative 2, negative 1. So negative 2. Where is negative 2? 1, 2. Negative 1. Okay, so it's going to go parallel to that. And then in between, it's going to kind of like slope off. See if I can get that a little better. So it's going to kind of go 1, and then it's going to get closer to 1/2, and then get closer to 1/3, and it's going to kind of go like that, and then here it's going to go up here, but then it's going to be undefined right there. Okay, and then we're going to go through the point 2, 2. So it's going to be here, so we're going to be parallel to this one, and then it's going to get more steep. And as we come this way, it's going to get more and more steep and get undefined right there. And then it's going to kind of taper off into a slower slope. So there we go. Okay, now we're going to solve the differential equation for this one. So we got to separate the variables. First, we got to write this as dy dx equals 1 over y. So we get to separate the variables, and we get y dy equals dx. So then we're going to integrate, and we're going to find those. So we end up with y squared over 2 equals x plus c. Okay, we're going to multiply both sides by 2, so we're going to get y squared equals 2x plus c2. And then we're going to get y equals plus or minus the square root of 2x plus c. So this is a square root function or a radical equation, and is that what we graphed? Yeah, absolutely. This is a radical, right? You may have recognized that from your parent functions. I hope you recognize that from your parent functions. Okay, so we're going to write the function's particular solutions that pass through this. So we have two different functions, remember. We have the positive side of this, and then we also have y equals negative square root of 2x plus c. So the particular solution that passes through negative 2, negative 1, again, we're going to use the negative version for that because I'm going to plug this one into that one. And we're going to plug this one into that one because our y value is negative, so we're going to use the negative general solution, and then if our y value is positive, we use the positive general solution. So we'll start with the blue one. Okay, so we have 2 equals the square root of 4 plus c, and then we square both sides and we get 4 equals 4 plus c, and we get c equals 0 because we subtract 4 from both sides. So our particular solution for this one is y equals the square root of 2x plus 0, which is just 2x. All right, now this other one, we're going to go ahead and plug in y equals negative the square root of 2 times negative 2 plus c, and I forgot to plug in my y, so that's going to be negative 1. Okay, so then I square both sides and I get 1 equals, that's negative gets squared, the square root goes away, and I get negative 4 plus c. Okay, hopefully that wasn't too big of a jump. We add 4 to both sides, we get c equals 5. So our particular solution for this one is y equals negative square root of 2x plus 5. So that one is the particular solution for this one we drew up here. And again, they match those graphs that we wrote, right? This is a radical function that's reflected over the x-axis with a shift of, would that be 5 halves, and a horizontal stretch compression. It doesn't matter. Anyway, we graphed these, right? These actually match the things that we graphed, so that's a good thing. Okay, the last one's, which of the following differential equations below matches the slope field shown at the right? So you just have to start thinking about different things. Now, what I do notice about this one is it doesn't seem to matter what x is. Y always seems, it seems to be the same slope on every y. So that means this slope probably doesn't depend on x. Okay, this one probably doesn't depend on x. So that's my first clue. And then the next thing I'm going to look at is, so that one's going to take out this one, and this one, and this one. And then what else could we look at? Let's see, y prime equals y. So that would be at when y equals 0, this should be a 0 slope, but it's not. It looks to be like a slope of maybe not 1. Yeah, it doesn't look to be like quite like a slope. Maybe it's a slope of 1. Yeah. So that doesn't quite make sense. So that one's out. So basically the only one we're left with is this one. And then we can check. Let's see. 0 squared is 0 plus 1. Yep, has a slope of 1. And we come over here to 1. 1 squared is 1. Sorry, this is still y equals 0. That's x equals 1. See? Oh, man. Okay, up here, y equals 1, right? 1 squared is 1, plus 1 is 2, so that looks to have a slope of about 2, about 3, 4, and you can see that. And it was not quite 4. You know what I mean? Maybe not. You're like, no, I don't know what you mean. This is really hard. Okay, last but not least, we're going to look at this one. And so the first thing I notice is there seems to be a very specific pattern to this one. So that kind of gives me a clue that this is going to look like one of these things. So does it look like an ln function? No. So I'm just going to get rid of those automatically because it doesn't look like an ln function. And so then does it look like e to the x? Yeah, but does it look like negative e to the x? So that would be it would change all of our y values. So it'd be like reflected over the x-axis,